Hi, everyone. We're live with Jeannette Wing, and I'd like to welcome you to CSTA's interview series, What is Computational Thinking? The goal of this series is to gain perspectives on computational thinking by meeting with leaders in the field. My name is Fred Martin. I'm a faculty member in computer science at the University of Massachusetts Lowell. I'm university representative to the board of the CSTA, and I'm the incoming chair of the board. Pat, would you kick us off?
Sure. I'm Pat Phillips, member of the CSTA Computational Thinking Task Force, a retired computer science teacher and editor of the CSTA Voice newsletter. Today, we're delighted to welcome Jeannette Wing. Jeannette is Corporate Vice President at Microsoft Research, and hearty welcome, Jeannette. Fred and I have a set of questions to get our conversation started, but first, would you please introduce yourself and maybe tell us a little bit about your background and your current position at Microsoft Research?
Sure. So thank you for having me, Fred and Pat, and all of you out there in the audience. I'm Jeannette Wing. I'm currently Corporate Vice President at Microsoft Research. What that means is I run the basic research labs at Microsoft. Before I joined Microsoft only a few years ago, I was on the faculty at Carnegie Mellon University for decades, and I was department head of computer science at Carnegie Mellon University twice. In between my two terms as department head at CMU, I was at the National Science Foundation in charge of funding research in computer science across the country. Does that help?
Very good. Thank you.
That's pretty amazing. Jeannette, thank you for being with us. We'd like to start our conversation today by asking you, how would you explain what computational thinking is if you were meeting with a class of third graders?
Well, first I would say that computational thinking is a way of solving problems where you could, let me see, how do I want to say this? You could have the solution of that problem executed by a computer. Mm-hmm. Now, the computer could be a human or it could be a machine. And rather than be so abstract to a bunch of third graders, I would actually pick on one of the third graders and I'd say, pretend that one of your friends is in the kitchen at your home and you want to instruct your friend to bake some chocolate chip cookies in the kitchen in a very precise way so that you're starting out with nothing and at the end you get some cookies. The idea then is, as the third grader I just picked on would try to instruct his or her friend in the kitchen to bake cookies, this person would be essentially describing an algorithm, describing a way in which to accomplish a task that a computer, human or machine, could carry out effectively. So I would not try to explain to third graders, this is what computational thinking is from a computer science professor's point of view, but rather get the third grader to think computationally.
A good answer. Thank you very much. I'm sure that the teachers in the elementary schools that are tackling this challenge of engaging their students in computational thinking have faced the same kinds of, now how exactly do we do this?
Well, I think if I may just elaborate on that, you know, there's already evidence, and I think my favorite example is the CS Unplugged work that has been around for many years already, which teaches children how to think computationally without machines. And it is about having the children be the computer or be the process that executes the algorithms, and it helps the children learn the concepts in computer science, which in the end is all about what computational thinking is about.
Indeed. Thank you. I know that
I can't hear you.
There was an echo. Try again, Pat.
Okay, I'm sorry. I know that you've been involved with computational thinking for quite a while. I remember your first essay. I'm not sure it was 10 years ago or not, but I'm kind of...
Jeannette, you had an essay like reflecting on 10 years, right?
So the article I first published was March 2016.
Yeah.
I mean, March 2006. And so this past March, I published a blog post on computational thinking 10 years later.
Could you summarize just a little bit how your thinking about computational changed over that period of time, and then we can point people to the second essay also.
Well, my thoughts about computational thinking has not changed at all. What I said 10 years ago is still what I believe in. I think what has changed are two things in my mind. First, I have come to be able to better describe what I mean by computational thinking, at least to the scientific audience. And let me just get this off my chest, because I did not say this in my article in 2006. To me, computational thinking is the thought processes that one uses to formulate a problem and to express its solutions, and there could be more than one solution to a problem, in such a way that a computer, human or machine, can effectively carry out. That's actually quite a loaded definition, because as we in computer science know, words like expression and effectively, and even what a formulation of a problem and solution are, those are loaded terms in computer science. But I think the main point I want to convey is computational thinking is about the thought processes that one goes through before you even write some code, before you're even creating an artifact.
I love the way you're pointing your head to make that really clear.
That's the one change. The second change is something that I did not anticipate, and that is the embracing of this idea of computational thinking by the broad community, nationally and internationally. And probably the most surprising and gratifying changes is the embracing of this concept at the K through 12 level. So when I first wrote my little paper, I really was speaking to the computer science community, especially the research and education community of the computer science population, saying, you know, we have a way of thinking that is going to transform the way all other disciplines conduct their research, and we have ways of thinking that can benefit all graduate students, undergraduate students, and so on. What I didn't anticipate is how this vision would really, in just 10 years, get reach the K through 12 audience. Of course, I imagined that because my vision was about computer science or computational thinking for all, and that, of course, has a consequence for K through 12 education. But I didn't anticipate in 10 years we would be as far along as we are now. By the way, I need to thank CSTA for that, because I think without CSTA, the organization and the teachers that are reached through CSTA, we would not in the United States have come as far along as we are now.
Thanks, Jeannette.
Thank you.
I'm sorry I cut you off, but I wanted to say I love the way you're pointing your head to make it clear computational thinking is a human process.
Right.
I want to welcome Irene Lee, co-chair of the Computational Thinking Task Force, who's on the call. Maybe Irene will ask something later on. So Jeannette, our next question is, how do you see computational thinking as distinct from other thinking skills?
So that's a great question. First, I want to say how they are similar to other skills, and then I will say how I think computational thinking is distinct. Because computer science draws on mathematics as its underlying foundations, it is what gives computer science the tools and language for expressing our foundations of computability and so on. Obviously, computational thinking overlaps with mathematical thinking, just in terms of modeling, abstraction, reasoning, logic, and so on. Computational thinking also overlaps with engineering thinking because, after all, in computer science, we build things. Just like other engineering disciplines, we build things. And we build things to work in the real world. So we have to work within real world constraints. We have to work within cost constraints, just like any other engineering discipline. So computational thinking overlaps and draws from both mathematical thinking and engineering thinking. But computer science is distinct from all other disciplines. And what makes it distinct from all other disciplines? Software. Software is a different kind of artifact that when we build software, we don't need big industrial plants and manufacturing plants to build software. And software has characteristics that are unlike any other engineered artifact. It's easy to create, it's easy to copy, it's easy to disseminate, it's easy to edit and manipulate and so on. Much easier than any other kind of engineered artifact. And so software distinguishes computer science from any other discipline. Now, the other thing about software is that you can do anything in software. You can build worlds, virtual worlds, that in these virtual worlds defy the laws of nature, defy the laws of physics. And so the creativity that one can explore in software is only limited by the creativity of human thought.
Very good distinction. Thank you very much. We'll have many teachers watching this video, and they've learned a lot about computational thinking from your presentation today, as well as some of the other previous speakers. And I think they're probably wondering how they might assess computational skills, and maybe even the basic of what does it mean to assess computational thinking, and then how can teachers do that in their classroom?
Well, I am not an educational scientist or a learning scientist or an expert in this. To be honest, I'm a researcher in computer science, and I know about computer science, but I don't know very much about assessment, especially at the K through 12 level. What I would imagine, I could give a simplistic answer. In the end, what you're going to teach in the classroom are going to be certain concepts in computer science. For instance, I was alluding to earlier what an algorithm is, or how to represent data so that you can ask questions about it efficiently and answer the questions efficiently. So I would imagine the way in which one would assess learning computational thinking is, first of all, for a given concept, do you understand what it is? And do you understand how to apply it? And this would be true of any concept you would learn in any science, engineering, or math discipline. Have you learned the concept, and do you know when and how to apply it? And so then the question is, what are those concepts? And what is appropriate to teach at what level of K through 12, for instance? I think those are all questions that we're still working out as a community. Again, I think I can also, so that's a given concept. I could also imagine per grade level, there are two ways in which one's learning of a concept or computational thinking more generally can be assessed. So for instance, let's take just one concept, algorithm. You could imagine at earlier grades, you don't have, you maybe perhaps give an algorithm, I mean, actually, I don't want to preclude any possibility because I don't know how third graders think. I don't know how seventh graders think. I think there's a huge debate over, is it too early to teach a particular concept or not? We don't even know that in math, and I don't think we know that in computer science. But I do think, analogous to all other disciplines where we do structure curricula over a given set of concepts, a level of abstraction per concept as you progress in your grade level, a level of sophistication of understanding that concept, and also just the number of concepts. All of those I can see from K through 3 level, you learn a few concepts in a concrete way. As you get to high school, you may be even learning the same concepts, but in a deeper way, and you're certainly learning new and more concepts. Does that make sense?
Sure.
Yes.
Absolutely.
It's a great reflection of what you described as what's represented in the CSTA standards that are the new ones are coming out. So thank you. Thank you for that little plug on the slide.
Jeannette, so you introduce yourself as a researcher. Can you describe what you would think would be the future of research in computational thinking?
So that's a great question, because what I think still needs to be done in terms of, and by the way, the phrase computational thinking, I don't think really is meant to be a research area. It was really meant to be a phrase that stands for thinking like a computer scientist, where the thinking part was the important part. And I certainly don't mean to say you can think like a computer scientist without knowing any computer science. At the same time, I don't mean that you need to study computer science to be able to think computationally. In other words, not everyone needs to learn all of computer science in order to think computationally. And I think there are a few concepts, yet I feel there are a few concepts that can benefit everyone. So now the question is, what's missing? Where does the research have to go? And I think it really is in the education space. I think for me, if you're an undergraduate, regardless of what major you're in, let me start the higher grades. If you're a graduate student, certainly in any science and engineering discipline, you're going to need to be able to think computationally just to do your own discipline. This is how science and engineering has already changed. We have talked for decades about computation being a third pillar of science, along with theory and experimentation. So this is a given. If you're in any science and engineering field, you will be using computation in your repertoire of research tools. So as a graduate student in certain disciplines, it's just a given. At the undergraduate level, I'm seeing such interest by undergraduates, again, regardless of major, because the students realize the importance of technology and the computing technology and the importance and prevalence of this technology in their lives. And so they know, they're speaking with their feet, as we can see with the enrollments in computer science at colleges skyrocketing. So I actually think at the undergraduate level, check. Computational thinking for all, we're there. So the question now is the K through 12 level. And there is wide open territory in terms of research. We do not know, for instance, what are the right concepts to teach at what age and how. So my analogy is to mathematics. Somehow we have figured out in mathematics, By the time you're 5 years old and you're in kindergarten, you have a sense of number. You know what the sense of greater than, you know this is greater than that. You have other understanding about numbers in general. By the time you're in 12 years old and you're in 7th grade, you have enough mathematical sophistication to learn algebra. Or at least that's what we think. We've been doing that for decades. And by the time you're 18 years old and you're in 12th grade, you have enough mathematical sophistication to learn calculus. So somehow we have figured out in mathematics the progression of concepts in mathematics, that from year to year you build on the concepts you learned in the previous years, and this progression of concepts reflects the level of sophistication and understanding that a child has as he or she grows up. So we somehow think that for most students, teaching algebra to a 5-year-old would probably not make sense. But to a 12-year-old, it makes sense. So what we do not have in computer science is this analogy that we have in mathematics. What is the progression of concepts? And I ask questions like, when is the right time to teach recursion? Recursion is not, for some people, an easy concept to learn. Is it when you're in 7th grade? Or is it something that a 2nd grader could understand? After all, language is recursive. And children speak sentences like he said, she said, he said, she said, and these never-ending sentences. But maybe the concept is too abstract. I don't know. We don't know. And another example is we do teach long division to 4th graders, to 9-year-olds. Long division, in the way we teach it in mathematics, is just an algorithm. It's just one way to divide one number into another and get a quotient and remainder. My guess is that for the most part in the United States, we teach one algorithm to do this. I don't know how math is taught these days. But if we use the word algorithm to 4th graders, we empower them with this larger concept of take 2 inputs, follow a procedure, and get 2 outputs. And by the way, you can check your outputs with respect to your inputs and so on and so forth. So, but we don't use the word algorithm when we teach long division. Why is that? Is it because 9-year-olds can't grasp that abstract concept? Or is it because we haven't dared to? And if we did, and we use that opportunity when we teach long division to teach the concept of an algorithm, then we would empower students to be thinking much bigger than they do today. So I don't know the answers to any of these questions, but I think the first and foremost is to get learning scientists, education scientists, working with computer scientists to figure out what is the sequence of concepts and what is the progression of abstract learning ability, sophistication in mathematics, engineering, and science, so that we can line up these concepts to the appropriate grade level. So that's one thing. That's a big thing. And I think we're ready to do that now as a community, worldwide, not just in this country. Absolutely. The second is we actually do have a very unique technology. It's called the computer. So how do we use this technology to most effectively enhance the learning and understanding of the concepts? And here's where I think we've not been thoughtful in technology-based instruction. We've just thrown computers into the classroom and thrown technology into the classroom and thrown hardware and software technology in the classroom and not been thoughtful about how to exploit this technology to actually learn fundamental concepts in computing and not just, do touch and gesture and, browsing and searching and superficial uses of the technology. I mean, after all, when you have a phone or you have some kind of device, and what I would love is for, a third grader to say to a teacher, how do you get all those songs on that device anyway? I mean, how does all that fit on that thing? That, if that third grader could just ask that question, it opens up a whole world of conversation about digitization of anything, be it music or books or documents or anything. And compression algorithms and storage capacity and battery power and just the design of a small device that can do more than make phone calls. So if that would be what I would like a third grader to ask, if we go back to your first question.
That's great. I think this might be a good stopping point.
Okay.
Jeannette, thank you so much for
You're welcome.
sharing all of your, and I love your passion and excitement about talking about it. I really appreciate it. Thank you for taking this time with us.
Thank you. You're welcome. Bye-bye.
Bye.
Bye.